About piecewise functions. It says that piecewise functions are defined in pieces. While some functions are defined by single formulas, others are defined by using different formulas for different parts of their domains. We've spent a lot of time so far this year talking about the domain of functions. So let's talk about what this might look like. Okay, so if we have this function y equals or f of x is equal to negative x if the domain is x is less than 0. So when x is less than 0, the function is y equals negative x. If the domain is between 0 and 1, the function is defined as x squared. And when the domain x is greater than 1, the function is defined by y equals or f of x equals 1. So let's just kind of take a close look at this. First of all, my first function I have here is y equals negative x, which you all should know, and I'm going to use the dashed line here. Well, I'll try to make a solid line. You all should know it's just that linear function that goes through the origin that has a slope of negative 1. And now my line is a little crooked, but that's okay. This is f of x equals negative x. Then we have the function f of x equals x squared. And we know that the points 0, 0, 1, 1, negative 1, 1, 2, 4, and negative 2, 4 exist on y equals or f of x equals x squared. And that would look like this. And finally, we have the function y equals or f of x equals 1. And that's just that constant function, that horizontal line that goes through the 1 on the y-axis. So that's basically all three of these functions here. But what about when they're restricted to specific domains? What we have here on the function y equals negative x, this function is only valid when x is less than or equal to, or just less than 0. So if I'm looking at this function y equals negative x, it's this entire line, but none of this part down here is included because I'm restricted right here to where x is less than 0. So that's this piece up here. This is the function y equals negative x when x is less than 0. Now looking at the quadratic y or f of x equals x squared. I'm restricted here from 0 to 1. So that means I'm from here to here. So none of this up here, none of this over here is included. So where I had the function y equals x squared, my entire blue parabola that I had here, the only part that I have is from 0 to 1. Just like, wrong color. Just like this. Okay? And then finally my constant function y or f of x equals 1, it's valid from where x is greater than 1. That means that every piece over here is not included. And this piece in between here and here is also not included. So now what I have remaining, this graph, is now this piecewise function. It is negative x when x is less than or equal to 0, that's from here to here. It is y equals x squared from 0 to 1, which there should be a little more of a, don't want you to think that's a constant, it's kind of got that curve, that parabola shape to it there. And then when x is greater than 1, we have our red line here, our constant function. And this is basically how you would graph a piecewise function. Now there are going to be some items that you're going to be graphing for your assignment and maybe on the review and the test that will require you to use a graphing calculator to maybe graph and then sketch. But what you're going to have to do, these types of functions here, like negative x, x squared, and 1, these simple types of functions, I would expect you to be able to graph those by hand like I did here. And then finally, let's look at a piecewise function graph and see if we can determine the domain. It says, given the following graph, write the piecewise function. So that means we need to actually write each function, each piece, and then show its domain. So I have f of x equals. So if I look over here from the far left, I always want to read from left to right. Looks like we have this point at negative 1, 1, and it looks to be linear and it goes straight down to the origin. Hopefully you can see that this piece of the function here is just negative x. And that domain is from when x is greater than or equal to negative 1, because I have a filled in dot here. And then it's going to be less than 0 because I have an open circle right here. So my domain is going to be x is greater than or equal to negative 1 and less than 0. Again, it's greater than or equal to negative 1 because I have a filled in dot here, and it's just less than 0 because I have an open circle here. And then moving up here, looks like I have some discontinuity, a jump discontinuity here. Also have an open circle here, but it looks like it's a constant function. Looks like it's going to be y equals 1. The y value is 1. So it's going to be f of x or y equals 1 when the domain is when x is greater than 1. And it's just greater than 1 because, again, I have the open circle. And then less than or equal to, I'm sorry, this is 0. When x is greater than 0 because of the open circle here, and then less than or equal to 1 because I have the filled in circle here. And remember, when I'm writing these domains, I am talking about the x values. And I know this x value is 1 because of this ordered pair here tells me the x value is 1. And now it looks like I have another linear function here going from here to here, and I need to come up with the equation for this. And this might take a little bit extra work. If I want to talk about this function in y equals mx plus b form, you should be able to tell right away that my slope is negative because it's going down from left to right. And it looks like I have a rise 1 and a run 2 because the difference between these x values here, this x value is 1. So the difference between 1 and 3 is 2. And then here I'm only rising to the 1. So if I rise 1 and then I have to run 2, rise 1, run 2, it's going to be a negative 1/2. Negative 1/2 is my slope. So far I have negative 1/2 x. And I don't have my y-intercept yet. Well, this line is somewhere, it's going to, if it keeps going, it's going to intersect this y-axis somewhere over in here. But how do I get this point? I do know a couple of things. I know that the slope is negative 1/2, and I know that the point 1, 1 is on the graph, and I know that the point 3, 0, actually 3, 0 is not on the graph because it's open, but it would be on the line if the line continued forever. But I do know that the point 1, 1 is on the graph. So there's two ways that I could do this. One way that I could do it is I could use my point slope form of a line. Y minus y1 equals m times x minus x1. And I can always fall back on this because I have a point 1, 1, and I'll go ahead and rewrite that up here, 1, 1, and I also have a slope, m equals negative 1/2. It might be hard to see up there, but I'm going to rewrite it right here. So what I would do is I would plug that in. This is my x1, y1. So I would have y minus 1 equals m, which is negative 1/2, times x minus x1, which is also 1. And I can easily distribute, and I get negative 1/2 x plus 1/2 because of the fact that a negative times a negative is positive, bringing the rest down over here. Then I would add 1 to each side, and I would get that y equals negative 1/2 x plus 3/2. Now how did I get 3/2? Because I've got 1/2 plus 1, and if I have 1/2 plus 1, that's really 1/2 plus 1 over 1, and my common denominator is 2, so to rewrite a fraction making it with a 2 in the denominator, if it's 1, it's just 2 over 2, because 2 over 2 is the same as 1 over 1. It's the same as 3 over 3, 4 over 4, 1,000 over 1,000. I had 1 over here, so 1 plus 2 is 3 over 2. So I get my domain, or my function here, is negative 1/2 x plus 3/2, and that domain for this function is from 1 when x is greater than or equal to 1, because I have a closed circle here, and less than 3 because I have an open circle here. So this is how you would come up with this piecewise function from this graph. You would have to know what each piece is, and you would also need to be able to state the domain for each piece.